Or what up? Good morning and happy Eastern. Today we're gonna program Snake in x86 assembly. And I already did that yesterday for the ARM processor. We started in the first video and I had an Easter bunny, so today I got this thing. I think that's, for me, that's the Le Petit Pont sheep. And we're gonna have a good day. We're gonna do Snake. And obviously, if you are new to assembly or you watched ideally the 10 videos that I posted or will be posting and are interested in assembly, that's a great and fun project to do, especially at the beginning. And that's why I also wanted to do it. So, well, let me first show you what we're aiming for here. So I have this somewhere here. Let me show you. So this is more of a, as I said, 100% vibe, 0% AI. So coding assembly Snake in x86, and oh well, we're kind of like this. Not really. Let me show you another one. Video x86. That's more what we're aiming for. What you saw there was the scoreboard. I was experimenting with it now 2 days ago. But as you can see here, we have the basic of the Snake game. You can control the snake, you can eat the food, the snake grows, if I can even do that. Let me grow here a little bit bigger, and then I can also start to kill the snake. If I can do that. No. Okay, I need one more food here, otherwise it won't work. So, no, uno más. We get this one, yes, and you can see the killing also works. So that's what we're aiming for. What you saw before is a scoreboard, which I might add at the end or on the GitHub repository. I should say that everything will be on the GitHub repository once these videos are up. But the scoreboard is a little bit of code bloat, especially the into ASCII conversion. And there are a few things we could tweak at the end, but this is the basic part that I want to do in the video. And it's like, I always like to quote Stephen Covey at this point, because he always said, like, the main thing is to keep the main thing the main thing. And for me, the main thing of the Snake game is to get something moving on the screen and have an input control and have everything done in assembly. I also want to say we are going to do this as fundamentally or as possible. So we're not going to rely on external calls or in stuff. We are just going to do syscalls and use the terminal as little as possible. So that's the idea, and that's what we're going to do. And so let me have here a sip of coffee. The sun is coming out a little bit. It's colder than it looks. I also want to say I have notes here, so we are hopefully not getting stuck entirely. And this part is for me always the scariest to get in, and I will obviously make mistakes. But I think we're just going to go into it and start right now. I'm going to go YouTube. No, is this correct? No? Oh, I don't have a thing here because this is the other computer. Okay, so let's make a channel. Or make a channel. Make a folder, and then we're gonna make here Snake x86. Now we're gonna start. This is gonna be a longer video, and I hope to get this over the Easter weekend. So I also should open this, have a good day here in the park, and then so that Le Petit Pont can he bite your ear off? But he's here, the companion now. Hit the trash. So if you want a highly optimized tutorial, that's not for you. You can go to the GitHub and read yourself. I have my sheep. Okay. That was what we're aiming for. The money shot. Okay. So let's set it up. Like always. Oh, see, I'm so good at this. So now we make this big. I will not copy and paste stuff in, but I have notes in case we're getting a little stuck, and I want to have the registers as close to the GitHub repository as possible, just to see that everything is close. But yeah, I hate if you copy something in and it's like, oh yeah, now I have to pause the video and read 10 lines, whatever. So let's go. A lot of we are setting up the standard here. Now let me get my head into x86 dot global start. Let's get a start label, move Q, whatever, I have no idea. RDE and RAX $23 in RAX and move Q 0x212345 into, no, that's not right, this is RAX, and oops, oh, the escape key is slow here. Wait, okay, no, because I'm recording, I didn't have a escape key. Scissor keys, keyboards, we don't need them back, and we're glad we have the escape key back. So syscall. Okay, so this should be okay, and we're gonna do a makefile for this one. So let's not talk, just do. The source is snake.s. The object file is the source file, but we're gonna replace the .s. Now we're gonna replace the .s with the .o file, and the target is gonna be just the base name of the source. Now here, this is as horrible as Python, that you have to have here, if that wouldn't work, but that does work. It's absolutely terrible. So we have the target. Now we're going to do the object file first. So $object, and what we need is obviously the source, and then we have to assemble. Arc is x86-64, and the output is this, and the input is just one file. All right, and now for the target, the same thing. Here we need the object file, and for the first few parts we can actually rely on the normal linking as static. We have an entry point start, and we're gonna do it static, which is not possible on the ARM architecture. Oh, it doesn't matter for this video. So -o $@ and $this, and now let me clean, remove -f target, and -f the object file. So this should be fine, right? It's always good if we have something going. Coffee. All right, so we're talking about, now I have to get myself in the mood. To explain everything I did yesterday again. So there are two ways to set up the playing field, and I pretend that's not there. Remind me later. Give me a window. Okay. There are two ways to set up the playing field. The first one is you make the first row, right? We go like this, and we do this 50 times because, well, in my version I always have the row as 50. So we would go 50, insert this, then we have the first row, then we would insert the first character, we would insert spaces, and then we would insert another border character that we would loop through this around this time, and at the end here we would insert the border. We are not going to do that, but I think this is a little unnecessary, and we're going to use an assembly directive to fill the memory immediately. Well, I can actually use that. So what we are going to do is we're going to have the memory and then going to do exactly that. We're going to take it and initialize it with the pound symbol. So now all we have to do is go from not from 0 to the height, but from 1 to the height minus 1, right about here, and the same for the width, and then we'll delete this part, and we're gonna have the border as well. All right, that's number one that we're gonna do. The second part is then when we have a playing field and we see it like this, we always think about it like an array, right, with a width and a height, or a two-dimensional array. In memory, that's of course not the case. In memory, you just have one continuous blob of memory. And what we have to do is insert here the \n at each character, right, like this. I just can't see somebody complaining that I don't have a Vim macro here. Okay, so this is what we're going to do. We're going to insert the You're going to insert the \n character. You're going to insert the \n character. So in memory, this part will always be with +1, and the +1 will be the \n character. So that is number one. And I think that's what we're going to do at the very beginning now. Makefile is fine. We are here. You don't need this. So let's go and say initialize playing field. And then end initialize playing field, and now we're going to get into coding with a little boilerplate. Push Q, RBP, move Q. Now in this direction, so we're gonna in this direction, so we're gonna move RBP into RSP. Absolutely not. We're gonna move RSP into RBP. At the end, we're gonna do the opposite. And then we're gonna pop RBP and return. All right. So the first thing what we're gonna do is do the data section here and do the assembly directive to fill the memory. So how do we do that? We need a thing. So I called this screen buffer. I'm going to use the fill directive. So now we need a size here, and we're going to call this buffer size. I think I should check the naming convention here. Buffer size, we're going to use that with 1 byte, and we're going to put in a symbol. And the symbol is the pound symbol. I cannot see if I have a comma here. I put a comma here. So let's define this up here. So the first thing we're gonna do is the height and the width. So we're gonna height, height is gonna be 15, but I'm gonna use the width here first. The width is gonna be 50. And then we have the screen buffer, the buffer size is gonna be width plus 1. Again, this is gonna be here the \n character, so it's gonna be width plus 1 times height. And that should be the buffer size. Oops, we should probably get rid of this. Move QF here, that's not existing. Move QF. Okay. What else was here? Oh, the symbol. Oh yeah, symbol is not defined yet. So what's the symbol? Well, I have to look this up, but I think, if I remember correctly, it's 0x. Symbol is 0x23. So this is the pound symbol. We could probably use a directive here also, but it doesn't matter. So this should be fine. So now we are in the position, that we have no \n yet, but we have all of this again filled like this. And the idea for the initialization function is now to remove the inner part and add the \n part. So how do we actually do it? Oh, it's getting a little warmer. Thank you. Now let the wind stop, let the spring start. Okay. Playing field setup is basically the \n. Let's start with the new line character. Actually, let's do two things. We first do, I had this not in my notes, but what we're gonna do is take the print playing field function a little earlier, so we can at least see our blob of memory. So let's do that now. Print playing field. And end. And then I'm gonna push Q RBP. I could copy that, but anyways, RBP. It's a relaxing Easter weekend. So pop Q RBP, and we're gonna return. So now we're gonna use the syscall for write, and we're gonna write to standard out. And I have somewhere, I wanted to show you this on the GitHub, but I don't have it because I don't have internet here. So what we're gonna do is look at it in plain text, coding, or I could blend this in at the video. Maybe I do that, but maybe not. Coding assembly, macOS x86 now, and I think I have this here. Yeah, that's the table. So we have the write syscall, we have in RDE the file descriptor, which in our case is going to be standard out. We have the buffer location, that's our screen buffer, and we have a buffer size. We have all this, so this has to be RDE, RSE, and RDX. And we're going to do, okay, let's first start with defining here our syswrite. This is 0x2, 1, 2, 3, 4, 5, 4, 5, 4. I have 5 zeros now. 1, 2, 3, 4, 5. Yeah. because it's the same for the X. The file descriptor is in RDE. Do we need, oh, we need buffer size we already have. Do we need anything else? So, where does the syscall goes in Rx? Yeah. So let's do move q syswrite into RAX, and then let's do the file descriptor is standard out. This is what I wanted to do. Let's do std out into RDE, std out RDE, and we're gonna define eq std out as 1. Std out as 1, we have the syscall. Alright, this is the better order. Now we need our buffer location in RSE, whatever I'm doing here, RSE buffer location. So we're gonna do layer q buffer, screen buffer it's called, right? Screen buffer rip into RSE, and the buffer size goes in RDX. So RSE, RDE, RDX, let's put it here. Fine. Move q buffer size into RDX. And let's compile it. Syswrite, there was something wrong. This should be fine. Hey. Oh well. All doesn't work if you don't call print playing field. So where is our segfault? First segfault of the start in what? Print. I cannot read that. Is this print playing fillet field? Okay. Nothing. Yep. Syscall. Need a syscall here. So let's do that. And we have something. That's okay. So this is the blob of memory. And now we're going to format it. And we already see it. I killed the cheap. Le Petit Prince. The cheap you want is in that box. It's like the breakdown of this program is get the playing field, clear the screen, initialize the playing field, initialize the snake, and clear the screen. That's the goal. And then the next time we're going to move the snake, and after that we're going to control the snake, and then we just do the rest. What's the game plan? So it's all this is hopefully over the Easter weekend. So we're here, we have our thing, and now we're gonna do the thingy here. Where is it? Initialize playing field. So we need the new line character, and now I want to look here what register I used. We have the screen buffer in RAX, the new line. Oh yeah. Oh no, this is for the offset. Yeah, okay, we can do that. So the difference between, well, one difference that you notice between x86 and ARM is how many immediate modes they have. So what we're gonna do is layer Q, the screen buffer, rip into RAX. So now we have the address of the screen buffer. We could add the width of the thing. Do I do that? Oh no, we do. Okay, even better. Yeah, we do move byte, and we use RAX as the address and the offset of the width of RAX. And now I forgot what I want to put in there, and what I would put in there is the new line. Is that a dollar sign? I cannot read that here. Okay, so this is the RX has the address and the offset. I don't remember how this addressing mode is called, but the width will be added to the RX, and we are right there. But it cannot work because for a function to work, you have to call it. So we're gonna do that and try again. And there we are. Here we have our offset, the first line, and now we have to do a loop starting somewhere at 1. So, what does the loop count is in RDX? Okay, whatever you say. 1 go gets RDX, and then we have our column loop and then the row loop. I changed the color scheme, by the way, so it's all blue now instead of all black for this video. Like, there is no winning. Can I get this a little bit? Be careful. No, it's already, brightness is all up. Okay, so we have to deal with that. So now this is the RDX is going to be the loop counter. We have the base address is still in. No, where did I do that? Was I not screen buffer in RSE? Didn't I put this in? I'm completely wrong, am I not? Print playing field, what am I doing here? I'm completely wrong. That's the only downside when you can't read here. Okay, we have to be here. I'm gonna move, we're in the function, we're moving 1 into RDX, and we're gonna start the row loop, and we're gonna end the row loop eventually. Okay, so we have the one we compare with, we're gonna do, this is all, I was a little confused there yesterday. We're gonna go from 0 to height -1. Now we're going, because we're gonna from 1 to height -1. So we're gonna compare Q here. RDX, now the other way around. Height -1 with RDX. Not branch, but jump equal, and no Q to end row loop. Okay, and we need the empty space in some register. A symbol EQ empty space, and that's 0x20. But let me check. Empty space is 0x20. That's correct. Initialize playing field. And we have the RBX gets the width +1, and we don't need an offset here. Okay. Yeah, that's time now. But I want the width +1 is okay. Well, or the empty space. That's what I wanted to look. Where is our, oh, we used the immediate. It's okay. So this thing, this we don't need. We need this here. Now, from in our screen buffer, this here is going to be 0, this is going to be 1, this is going to be 2, and so on and so forth, till 14 here. And the same for the row, of course. Yeah, 1 until 49 here, or 49 will be this little symbol here. The last symbol here would be 49, and this would be 50. So why is this important? Because like I said, in memory, everything is a continuous blob and not an array, but we can access everything if we're going take this 1 time, 2 times, well, 0 times we're here. 1 time we're here. 2 times we're here. 3 times and we're here, and so on. So we can go to the beginning of each row with width +1. Again, the +1 here is the \n times y. Right? And then once we're at the beginning of the row, we can add the x coordinate. Like this, or like this, well, whatever. So like x. So this is how you go in memory represent the 2x2 matrix here. And we are going to need that not in a moment, because we want to insert, we want to have the row number, we're going down the rows, and then we're going to go across. While we're going to have here an inner loop. We have RDE for the outer loop counter, or we can call this probably the row loop counter. And now we're gonna calculate the beginning of the row, which would be, we need the width +1, move q $+1, and the width +1 I placed into RBX. All right. So this is the width, and now we have to do the multiplication. So where is it? We have to get width plus the y, which is the loop counter. We're starting at 1, so we will start here. So let me do that. I'm gonna do that right about here. Okay. We're gonna take RDE, that's our loop counter, into RCX, because once we multiply in x86, we lose our stuff. You probably know that. So I multiply the width q, which is in, this is a b, RBX, and multiply this now with RCX, and then we have now width +1 times y, and now we have to add nothing. Right? We have the width, but we are not at a screen buffer. We have to add. Let me put my brain on here. So ADE is the loop counter, but it's here RDX. RBX. Oh, here I have the offset in. So multiply RBX with RCX, and RBX is width, and CX is not the loop counter. Oh, this is correct. RCX. We don't need. Well, let me think here. 1 second. We have our width in RBX. We want to have RBX times. Really, we want to have it times RDX. And then we have, but we lose our loop counter, so let's put RDX into RCX and then multiply by RCX. So now we have width plus 1 times RDX and RCX, and that means we are at the beginning of the row. So we would be right about here. And now we need the row loop counter. The problem is here I have the scoreboard offset in, but RDX is gonna be the row loop counter. We have not used RDX. What is okay? I have it's all good. I understand. I had this as, and I will change that. I have this here as RDE. So we have this as RDE. So we have RDE goes into RCX. So this is the row loop counter. We put this in RCX. This stays the same. And now we're gonna initialize the row loop counter. Yeah. So that's the row, that's the column. I don't know. Like there's some you get confused with the name here. It doesn't really matter. We have one in RDX, so this is the one we're going to go across. Column loop and end column loop. Now I almost want to change it. So what is the logic? You can say I don't know. What the column? Now I want to almost change column and row. I'm not gonna do that right now. So we have this, and we're gonna put the empty space. We start at 1, so that means whatever the naming is, we're starting right here because the loop starts at 1, and we're gonna get the loop up to compare Q or compare. We can do compare Q with height -1 with RDX. So this will be the moment we are at this position, height -1, and here we're going to do jump equal to end column loop. There are colon and column loop. All right, and now we're going to put the empty space in, and we can use here an immediate mode. So we're going to move byte, the empty space, to wherever the screen buffer is. The screen buffer is here in RAX, and we're going to use the offset that we calculated here at RCX I don't think we can, so we have to do the addition. RCX and no, where's RCX and do the RDX? Yes. Oh, I didn't. Okay. So we calculate at this point in the loop. We calculate the width plus width plus 1 times y. So we are every time we start the row loop, we are in the row. So that's why we call it the row loop. So like it's so here we are going into this row, and then we're gonna loop in the row. The naming I hate with these things, but it makes sense. And so we start at 1 and we go to here and we place the empty space in the loop. And this here we have the screen buffer calculated already, the offset, and then we always add the RDX. And when we start the loop, we're gonna reset it to 1. So in the loop, we obviously have to add 1 to, or we can do here. I should do that. Increase Q RDX by 1. And once we finish this loop, or we have to branch as well, but once we finish this loop, we have to increase Q RDE, and here we have to jump to the column loop, and here we have to jump to the row loop. Do we have a condition here? We don't have a row loop condition yet, so let's add that also. So compare Q, CMP Q, the number, once we are at height -1, this is completely wrong. This is width -1. EDTH -1, and here we're gonna do height -1 with RDE. So let's check that. Well, we have to jump equal. Once we're there, we're gonna jump to end row loop. So let's go through this here one more time. The RDE is our row counter. We check from 1 to the height -1. Once we're there, we are finished. Every time we calculate RDE times RDE here, we put the RDE in RCX and multiply RCX with RBX, RBX being the width plus 1. So we are every time at the beginning of the row. Then we initialize the row, this is like the column loop. Column and row I would interchange. Now I'm gonna do it. This makes no sense to me. Column, what I did here. Column, loop, and this here has to be the row loop. And I cannot confuse myself here. And so this is row, this is row, and column, and column loop. Okay, because here we are looping through the row. So we have from 1 to width -1. Once we're at the end, we stop, and we're going to put the empty space at RCX, and that hopefully is fine. And we have to debug that now. I'm gonna have a problem here. An argument list. Move Q $1. What row loop counter? Oh, we have, this is not a comment here. We have to have the ugly comments. Okay, that's that. And end row loop is already defined. Inline 50. Oh no, this is gonna be fun, ain't it? And column loop. Come on, give me something. Where's the segfault? Yeah, of course. First segfault of the day. Where's the coffee? First segfault of the day. And we changed column and row. So let's go. Let's check this one moment here. We have the screen buffer and RAX. That's all fine. This part is also fine. We have RDE here. We have this in RBX. We start the column height -1 to RDE. That's all fine. Did we add? I increased, I hope, increased RDE. So we are counting through it. That's okay. So RDE has, we're gonna move RDE. So if it's 1, we're gonna move it into RCX, and then we're gonna we calculate RCX times RBX, which is gonna be width times 1 time. But somehow we have to add. This is a number. This is not an address. So we have to add here. Where's the RAX to R? Oh no, we don't want to do that. We have the offset. We're doing this here. This is fine. Well, this is just the offset without the address. So we have RDX here. And no, we want the offset here. Did I do this here? Yeah, we want this. RDX is only the row offset. So we want here add Q RAX RCX. So this is the pure offset width plus 1 times Y, so a number. And now by adding this to the address, we have the actual address here in RCX, and then we're gonna add another offset to the address for the single bytes in the row. And there we have 1 row. So that means, oh well, no, this is all fine. We did this, and we also jumped, I think, here. But what we did not do is skip the 1 border part and include the new line character. So we did now this, but we didn't do the new line character. And that is what we have to do after the row loop. It's like, whoa, oh, we have melted chocolate. Melted chocolate. That's not good. Put it here in the shadow a little bit. Okay, so we are by width times 1, and this is our RDX. Right about jump row. So after the row loop, first row, second row, yeah. After the row loop, now I'm gonna get myself confused. We can increase RDX 1 more time. So that is to skip the border part. And then we place move byte byte new line also into RCX RDX. So let's test this. Unexpected token. Is there no comma? There's no comma. And still no liftoff. You have the increase. We are in the row loop. Yeah. We are not doing this. We're at the end. One second, then I'll check my notes here. But we're in the row loop. We put we are looping through. Put the empty space in. We move here. We increase RDX to put the thing in, and for some reason we do not have jump column loop. Okay, let me check. You have one. Did I add it to the wrong thing here? No, RDX, that's correct. 1 to RDX, add new line, and row loop, jump, row loop. All of this looks fine. We have one more increase RDX here one more time. Now that doesn't do nothing, so we have to check that. Jump column loop, we are here. Also not like to put this actually in line here with the thing. Compare height with RDX. Why is this here? Oh, I had this before. Yeah, like the black screen is not good here. Row loop compare. We are increasing RDE. Do I overwrite this again? RDX. But we are putting RDX here into 1, so this should not matter. And row loop. I think I'm gonna check that out. So let's do that real fast. We are initializing the playing field right about here. Oops. So let's check that out. Oops. And now it doesn't give me a breakpoint. Call initial. Oh, this is again this thing. Yeah, for some reason, initialize playing field LLDB doesn't like the first address. So let's run it. So we're here in the function. We can see register read RAX. That's the screen buffer. Why are we in print playing field? Did I have the wrong address here? playing field, initialize playing field. We want to be right here, right? Is this still working? So break set minus address, a little bit of stuff. So here we are. I'm at end initialize playing field. That's the problem. The snake. So let me get, we can go right about initialize playing field. So this is where we want to be, and nowhere else. Okay, push the thing. We have the screen buffer in RAX. Replace the new line. There's the read RAX. We can also check this out right about here. This should be 64 or something. Oh, let's do 128 XP. There's our initialized screen buffer. That's all fine. We have RDE, RBX, register read RDE. That's a 1. Jump equal. We're not equal, so register read RCX. CX is 0, but now it's also 1. Compared with register read RAX. Here's the screen buffer. Where is add Q RAX RCX multiply. Okay, yeah, this is fine. Register read RCX is what it does. So this is screen buffer plus 51. That is exactly right. And now we have RAX plus 1. So that's so far we're good. The question is, why are we not getting the thing? So this is register read RDX. Also 1. Now we move the byte into register read RCX. That's the screen buffer RDX counts. And now we're gonna count through this. And now we don't wanna do that. We wanna go right here, set minus A. Here, continue. Okay, I have a suspicion that when I named this thing, we wanna end this to column loop. Yeah, that. Now, once the height is over, we enter the end of the column loop. The end of the column loop is right here. So once we are at the row, we jump to the end of the row loop. Yeah, they're naming this. That's why I didn't want to end this, rename this. Okay, that was the issue. So we're almost there. The only thing that you see here is this little thing missing out, just because of we are looping. Well, let me do this here. We're looping only through this part, and this part here we had to do at the beginning, and this part we have to do here at the end. So let us do that, and then I use buffer size -1 into RAX immediately. Yeah, okay, so in RAX here at the end is still because we the screen buffer address, the starting address. So now we can just, if this is a good idea or not, but buffer size -1, add this to RAX. Now we're at the end, and then we're gonna move byte a new line into RAX. And there we are. That's our playing field. A little wonky there for a moment, but I think the naming convention now makes more sense. I will change this here as well. Or I remember why it was the other way around the first place and leave it. Who knows at this point? And no, we loop for each column, and then we loop through the columns, and then for each column we loop through the row. This makes sense now. Okay, so we have this done for you print the playing field. Now we're going to clean the screen. That's done. There we use the terminal a little bit. We have to use an ANSI escape character, which we put here in the data section. So clean the screen. And we're gonna have this as an ASCII character. There has to be a dot here. And this is x1b something. Let me check this at least. This is gonna be x1b and a big H, and then x1b a big J. So let me also say this is one character. This is an escape. So this is 1, this is 2, this is 3, this is 4, this one is 5, and this one is 6. So this will be the length of this will be 6. So let's write the clear the screen function. Clear screen and end clear screen. Let me write a little bit of boilerplate. Move Q RSP into RBP, and here we do the opposite, and we pop Q RBP and return. And now we're going to use the same function as for our printing the playing field, wherever it is. Printing playing field. So we got to print the standard out. The buffer size is going to change to 6 as we just determined, but we're also going to write. And we need the escape sequence in RSE. So I'm going to copy this. Did I have this? Paste this here, and RSE I said, I hope. Layer Q, CLS, rip into RSE, and the buffer size we determined is 6. So this should be all. Oh, we're compiling. Now let's clear the screen. Call, or we can do, no, it doesn't matter. We can do that first. So call clear screen. Snake, yeah, we didn't do it. And that is that. All right. 2 functions down, 1 to go for this. And the last one that we're going to use is initialize the snake. So we have to clear the screen, we initialize the playing field, and now we initialize the the snake. Initialize snake. Initialize snake. Okay, so how do we store the snake? I wish I could blend that in. I have a README. That's README. So we have here. This is gonna be on the GitHub again, hopefully. Well, I'm writing it this weekend. So here, this is how we're gonna store the snake. We're going to use a circular buffer, and we have the coordinates always in pair. So x1, y1, x1, x2, y2, all the way to whatever coordinates we have. And then we're going to place a pointer to the tail and a pointer to the head. So these are two places where the address of the position of the coordinate buffer is. And each time we're going to move the snake forward, we're going to pull out, well, we're going to cross that bridge when we come to it, but we're going to pull out the coordinate, then we're going to get the position, the x and the y, in whatever direction we move, and then move the pointer one forward, and at the end, then move the tail pointer forward. So that's the data structure that we're going to use. I think I made for the ARM version, let's do that as well. I had the x1, y1. So we have like this, x1, y1, 2, 3. Oh no, we start, well, 3, it's okay, 2, 1, 2, 3. Let's do 4. And of course I missed the 0 part. So here we're gonna have the tail, and here we're gonna have the head pointer. So that's tail pointer, and head pointer initialized. So let's go right into it. I don't know. So the faster we are, the more time we have for debugging. That's the spirit here. Initialize snake, ain't initialize snake. Push Q, RBP, move Q, RSP into RBP, and then move RBP into RSP, pop the old one, and return. All right, so what we need our snake. I'm gonna make one label that I just called snake, and we're gonna have the coordinates. So coordinates, we're gonna fill this. I don't see what I write there. Fill with coordinate buffer size. I think was the creative name. Coordinate buffer size, exactly. Coordinate buffer size, 1 byte, and we're gonna fill this with 0. It doesn't matter. So that's what we have. Well, we need to define it. EQ coordinate buffer size. We're going to keep this small for now, but we always want to have it dividable by 2. And so we're going to do 4 times 25 for now. I'm keeping it short because I want to see then if the circular buffer works. Stay hydrated and keep the chocolate close. Okay, so we also want the head pointer now. This is gonna be 8-byte number because it's a pointer, and after the head comes the tail. I have to see if we're gonna rename the head pointer as well. Not the head pointer, but the head pointer is, it doesn't matter. Well, what I want to say is the head pointer is directly after the coordinates buffer, so we can use that like an iterator in C++, right? If you're gonna need the end of the coordinate buffer, we can just use the head address. But then you cannot move the head pointer in memory away. The head label has to be exactly after the coordinate buffer, so we might use two labels for the same address later. Or just leave it, and if somebody moves it, it's his fault. Okay, and initialize snake, initialize snake, we have it here. So the first thing we're going to do is put the coordinate buffer address at the tail, and then go 3, 4 forward, and well, the length will be, the initial length of the snake will be 4, but we're counting from, I made a mistake there yesterday, we're counting from 0, so we're gonna go 2 times initial length minus 1 and place the head pointer there. So let's start about here. EQ initial length is gonna be 4. New line, I did not want to do that. Let's place it maybe here. Okay. So let me check the registers. So the first thing we need is the coordinates, goes in R, and direction, and we can do that immediately. Where did I use R8 here? And head RBX is gonna be this, the tail. Okay. So we're gonna do what we said when I find where I am. Initialize snake. We should really use dark mode. Outside is almost unusable. So take the, well, we have the tail pointer, so we're gonna move the coordinate buffer, coordinates rip into RAX, and we're gonna place that address. Wait, coordinates is not the address. Layer Q is the address of the coordinates, and we're gonna place that address into the tail pointer, right, like so. That should be fine. Yes. And now we're gonna do the weird thing. We're gonna add to the address of RAX the initial length. Do I do that? Why is this not RBX? Oh, I want to keep it. Alright, apparently. Move Q. So I keep the address here of the coordinates in RAX, so we move it also in RBX, and now I add the initial length well, I'm guessing 2, because 2 times initial length, 2 times initial length minus 1. So this should be that into RBX. So let me, 2 times, the initial length is 4, but we store the coordinates in pairs. That's 2 times, and minus 1 because we're counting from 0. So we will have 0, 1, 2, and 3. And now we have this address in RBX. So RBX is now the address of the head pointer, and we're gonna move Q RBX into head rip. So at this point we have our buffer. We stored this address in the tail pointer, and we stored this address in the head pointer. We have not yet set up the coordinates that are actually at this place. That's what we're gonna do in a moment. One thing I always here forget, this is we also have a direction, but we use later, and we're gonna initialize that to 0. And now we're gonna set up, we're gonna move Q1 into the direction of the label. Coordinates, undefined symbol. In which line? Can you tell me the line? Where is the line? Undefined symbols. Initialize snake. Coordiantes. 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 Where's coordiantes? Coordinates. Coordiantes. Okay. Well, it compiles, but we didn't call the function. So actually, let us do that. Call initialize snake. Okay. Didn't crash, that's good. So we have this. So this should be set up now. And now we need, and I used R8 and R9. Yes, so now we're gonna set up where we actually, let me copy this here down. And remove this. So now we have to set up where we want to have the snake to start. So we're gonna go height divided by 2. So this would be here 15 divided by 2, 7.5. So we will end up at 7. That's where we start from the y coordinate, and the x coordinate is width. Width is 50 divided by 2, but we're gonna, if we start here, we would start to add the snake from there. So we're gonna go back the initial length so that the head, this is really not that important, but it's kind of bothered me. So the head will start in the middle, not the tail. Yeah. So let's just chill. So we're gonna start with that. So we're gonna take the width divided by 2. I don't know. Let's do this. Minus the initial length into R8. Okay. And then we're gonna do height -2. And we're gonna remove 1 here into R9. Oh, we have a automatic mower. Okay, so this should be fine. Now we're gonna use our symbol in R10, probably useless because we can use the immediate as well. Well, we did it here, so initialize snake. Where am I? Initialize playing field, initialize snake, and okay. So here I placed the symbol in R10, and then we placed R10 at the position that we're gonna calculate, but I'm wondering why not just use the immediate, because at least we are on x86 here. Well, let's roll with it for the moment, and then we can check if we want to change it. So because we're gonna go now to this position, we're gonna have to do 2 things. Store the X and Y position at the coordinates place, add 1 to the coordinate, go further with in the coordinate buffer, insert everything, and then insert the actual symbol at the playing field. This is the goal of this function now. So let's just keep moving. Symbol goes into R10. So we have this, and then we get a loop counter. Why ever I do this here, but doesn't matter. RDE, this is going to be a loop counter. Make here the comment, loop counter, and we cannot do this comment here. I love this comment and I hate this one. Pound for comments. And I always think this is the mower is some bag or something. All right. We have the 0 there, and RBX gets the width +1, so we can calculate +1 goes into RBX. So now we're going to calculate again our initial position. So this will be our R8 will be our X, R9 is our Y, so we need RBX times R9, and in what register do we keep that? In RCX again. Yeah, this is so we're gonna move the RBX into RCX, just so we don't overwrite it now, because we need that again. And then we're gonna add the Y. We multiply R9 with RCX. What's going on here? Multiply R9 with RCX, and now we're gonna add so maybe we make here also. This is width +1 times Y plus X. So now we have done RBX is width +1. We have this in RCX, and now Y is our height divided by 2. So now RCX is this part, and now we're gonna add the X. So if I get there, add Q R8 into, is there a comma? R8 into RCX. No battery, no. Oh, no, this is not good. Why do we have low battery? Okay, RCX, so we have to hurry here. We have this in RCX, RBX into RAQ. Okay, so now we add the RAX to RCX, so we have again the address. This we calculated the offset, and now we have the address, and now we're gonna go here a little bit, initialize snake loop and end. So I'm gonna do immediately the loop counter is when we are at the initial length, so initial length comparing with RDE, and if that's the case, jump equal, we're gonna jump to the end. And now in the loop, all we're gonna do is move byte the symbol into RCX RDE and move by symbol R6 RDE. That's putting it on the buffer, and now in REX we have the coordinates, and that's now where we place the actual coordinates. So let's move R8 move bytes, R8 byte. This is our X coordinate into RAX, and then the 9 into 1 RAX. And let me check here, 1 coordinates, that's the coordinates, and that's where we want it to be. Okay, so we have done that, and now we just increase. Well, we have to add 2 to RAX. Why 2? Because RAX is the pointer, and we have always the coordinates in pair. So we're gonna add 2 to RAX, and we're gonna use increase Q for R8. And did I forget anything? We need, oh, the loop counter. Okay, and increase Q, the loop counter. Okay, so anything else here? Okay, I think we're gonna try to run this here. 0 are invalid operand, move byte R8B. I just forgot the % sign. That's what you wanted to tell me. Thank you. Increase $RDE does not exist. So we have nothing. That's initialize snake. We have to jump, obviously. Jump initialize snake loop. However, we should see something. rbx, rcx, add q, rax should be the address here. rdx, move, we add it here to rcx, that's the offset. We are placing the then RDE. Did I have RDE? Where's RDE? RDE is 0. So RCX here should be, it should be placed right about here. Does he need here a 1? Do I see this? Now we have no time, so let's, where is initialize snake loop? Let's jump right to this point. Snake break set minus address here. So we have register read RCX. Register read RCX is the snake. No, this is not quite right, is it? This is not the address. Oh yeah, okay. Step. Now we're doing it, and now we have here the address at the snake. So this is fine. Let's check that. The battery stress is now real. So let's check this. Register read RCX. Register read RCX is this. This looks pretty legit. RDE 0 looks also legit. Wait. RCX is, where's the screen buffer? Where is the screen buffer? Print playing. We don't have the screen buffer. Where is the screen buffer? Coordinates. Yeah, we'll need the screen buff. No. Okay. This is all nice here, but we want to add here. Here we expect the screen buffer in RAX. So we should put it here, layer Q, screen buffer rip into RAX. That's when we have RCX, and then afterwards here we're gonna place the snake or the coordinates back in RAX. Okay. Let's test that. It's up to date. It cannot be up to date, buddy. There's the snake. Whoa. Okay. So hopefully we get this for the batteries. So we have, what I did here, we have the RAX and we treated here the RAX register as if this were the screen buffer, but it really was still the coordinates. So we place here the screen buffer in RAX, we do the calculation, we keep it in RCX then, and then we override RAX with the coordinates. So now for the loop in RAX here is again the coordinates, and in RCX is the screen buffer. So now let's LLDB, oh no, object dump minus the snake. Let's go one time to initialize snake, or let's go here, LLDB So if I break up, thank you for watching, and we will see you in the next one when we do the movement. But we're going in here. I'm gonna check, well, we cannot check the tail because we don't have the addresses, but we assume that works. So here's the screen buffer. So at this point, register read RAX, we have the screen buffer. That's all fine, which obviously works because we see the 4 symbols on screen. But now, what we didn't see, the read RAX, is the snake here. This is where the coordinates live. Remember, coordinates and snake is the same label. So let's check this. And this here now should be placed 15, 17. This is the first coordinate. So if we loop here through, we have the 16, 17, the next coordinate. We're not there yet. Increase. We have 17, 7 and one more. And 18, 7. So this is the coordinates are in our coordinate buffer. We should check this, but we haven't. But here we place the address directly into the head and tail buffer. So we have this address. So the tail would be this address, and the head would be this address. With this is 3, 4, 5, 6, 7, 8, 9. This address with the 9 would be the head pointer. All right, so I think we are at the end of the battery life. I'm going to show you the preview for next time. I'm going to eat here one more sheep, and I'm going to show you the preview. Document. So this here, well, this is not, where are we here? Direction should be 1. Wait, we want to have this for the demo. So this is the idea for next time, that the snake moves to the right and then loops, and then we do all the directions, but that's in the next one. So happy Easter again. I'm gonna try to get them all out over the Easter weekend. Thank you very much for watching. See you in the next one. Peace.